Okay, yesterday we talked about inflection points, and I finished off on this example. So we've got a vase that's shaped like this, water's coming in at a constant rate, and we've got our function that we're interested in is the depth of the water against time t. So, hello? Is that from somewhere else? Yeah. Okay. Explain the concavity and indicate the inflection points. And we already discussed this. If water's coming in at a constant rate, then if the vase is narrowing, then the height is kind of the rate at which it's filling up is speeding up. So we would expect a shape kind of like a nice concave up shape like this. Okay, we would start at 0 when we started filling it up, and it would speed up. And then after when the neck is expanding, it's slower to get to the same height, and so we would have something which was concave down. So we'd go something like that. And this inflection point here came here when the vase was the narrowest. Okay. So here we have an example of a function. How many inflection points does this function have? So, Peyton, what do you think? 3. 3. Let's have a look. So it's concave up, concave down, so there's one definitely there. But also we see that it goes from here, all of a sudden it starts concavity change around here. So 1, 2, 3. Yeah, I would agree with 3. So here is a function. Hang on. I believe. Yes. Oops. So now here we have a graph of the derivative. So it's not a graph of the function, it's not a graph of the derivative, it's not a function of the second, it's not a graph of the function, and it's not a graph of the second derivative, it's a graph of the first derivative. So how from the graph of the first derivative do we get it's an inflection point? Jay, would you like to have a guess at that? Yeah. Okay, so we go it through. How do we find inflection points? The derivative has to equal 0. So here is the only candidate for an inflection point, for f. Okay. And does concavity change? Yes, because it goes from negative to positive. Okay, so the sign changes. That means the concavity changes. That means it is an inflection point. Okay. F prime itself, of course, has an inflection point out here. But that's there just to, that's the trap in this question. Here's a numerical question. So remember, questions can come at you by a formula, by a graph, or by a table. So here, so we're interested in making 10 o'clock being an inflection point. This is a graph of yes, so what would be a rate if we had an inflection point at 10 o'clock? So this one's a little bit harder. So let's turn it into something graphical because that's something we can understand. So at 8 o'clock, 9 o'clock, and 10 o'clock, the derivative was 2, 3, and 4. So that means what's happening to the slope?
Increasing.
It's increasing. So it's something like this, right? So we definitely see something that's concave up. For this to be an inflection point, what has to happen afterwards? It has to sort of go down, right? So which one of these ones fits in it with the rate going down? A, right? Because it goes 2, 3, 4, it's increasing, it's speeding up, but then if it goes to 3, it's slowing down. So the concavity has changed. Okay, and here is kind of like just a word thing. So we have to, okay. So Joan has been working out. She's getting muscle, right? So when she started out, she was getting those muscles, but it was increasing at a slower and slower rate. But then she reached an inflection point. I don't know. She started doing something with the diet as well, and, really, really working hard. What happened after those 3 months then?
C.
Straight away, C. Anyone else anyone see any different? Okay, so it's an inflection point. So that means the concavity has to change. So beforehand, it was increasing, but at a slower rate. So this is the picture in your mind that you get. But all of a sudden, she has an inflection point. So it goes from concave down to concave up. It has to go like that. So that has to be the picture in your head. And it's increasing, but at a faster rate. Okay. Yep, that's good. Okay. So I hope everyone's got a nice idea of what an inflection point is. Okay, let's get on to today's topic. What is today's topic? It should be global maximums. What do I want to do? Let's put the board up. Okay. I don't like being restricted. Okay, so what have we done so far in this chapter? So first we had a look at the idea of the critical point and the idea of a local max or min. So this just means we've just got a little hill and we've got a little valley, and we've had a look at the idea of an inflection point. Again, it's to do with the derivative being 0. It's the second derivative being 0 this time. Okay, so you all kind of got it in your head. If I give you a function, a basic kind of thing you're going to do is you're going to take the derivative, set it equal to 0, find critical points, then take the second derivative, set it equal to 0, and find possible inflection points. And then you're going to go and you're going to look at the critical points, and you're going to analyze them, and you're going to figure out whether it's a local max or a local min, or it's neither. And then you're going to look at the possible inflection points, and then you're going to figure out whether they're actually real inflection points or no, we don't call failed inflection points anything. Okay, so that's, I think everyone's sort of got that idea in their head. Okay, the next thing we're going to look at is to go from the local to the global. So you all sort of know the idea of a local maximum, right? That just means you're on top of a hill. Global maximum means you're on top of the biggest hill. And if you think about it, this is something that you want to be able to do. If I give you a function and maybe some kind of interval or something, this might be a function which is telling you profit, or it might be giving you some good quality that you want to optimize, right? You want to know what is the best. And so that's why we're interested in global maximums and minimums. So let's do a definition. So a global maximum so f of x has a global maximum at x equals a means f of a is bigger than or equal to f of x for all x. Okay, and so hopefully you can see the difference between global and local. Global means for all x, local means just for x near A, for some neighborhood. And similarly, we say, sorry, I don't know why I put that there. F of x has a global minimum at x equals a if f of a is less than or equal to f of x for all x. Again, the difference between global and local means for global you mean for all possible x. Local just means for the x near A. Okay, so this is something desirable that we want to do. So we have to think of a way to find. How do we find global max or mins? Okay, we just have to do a little bit of logic. What's the relationship between a local maximum and a global maximum?
It's the biggest one.
Right. So a global maximum is also going to be a local maximum, but not all local maximums are going to be global maximums. Okay? But that gives you a list of candidates then. So the first thing you do is you find local max or min, if that's what you're doing, is to find the global min, you find the local mins. How do you test them? Let's say we have, x1, x2. Say we have we find a whole bunch of local maxes. How do we determine which one is the global?
You just plug it in.
Yeah, we have a test, right? We just put it into the function, and whichever is the highest, we just then do what? We just test them, find which is the max of f of x1, f of x2, etc., or the min, of course, if that's what we do.
this work for functions that go towards infinity or negative infinity?
Aha. So now you've got the thing. Yes, that's the problem. So we've got to worry about the domain. Okay. So let's do it the simple case first. Let's say on some closed interval. Okay. And to help us do that, there is a principle. I don't know what I'll call it. I'll just call it a principle. A continuous function on a closed interval attains its global max or min. Okay, so the case that Eric is worried about is this sort of case. Let's think of a nice simple function like x squared. Okay, so x squared goes like this. Right, so if we just looked at all real numbers, we see that here, we see its global minimum is there. Where's the global maximum? There's no global maximum, right? Because whichever number you think is big, you can go ahead and find something bigger, because it just goes off to infinity. So infinity is not a global maximum, minus infinity is not, because it's not an actual real number. Okay. But if, for instance, I say minus 10 to 10, and make it a closed interval, all of a sudden, those endpoints become the biggest values. That's where the global max is on that interval. Okay, so we have to kind of modify this a little bit. We did. So what are we going to add in? The endpoints. Find local maximum and add in endpoints A and B. And so to this thing here, we also add in f of A and f of B.
So those are both global maxes?
Right, so in this problem here, it's got two global maxes because yeah. So you're allowed to have more than one global max if it's the same value. Okay, so for example, sine x has got infinitely many global maxes because every time it reaches the top. And if we look at our principle, we see then that this is guaranteed to work. Right, because there has to be a global maximum in. We don't have the problem like over there. And the maximum in either has to be at a critical point where we've got like the top of a hill. And if it's not at the top of the hill, it's at an end point. So that's actually a pretty straightforward procedure. What if it's an open interval? So, for example, it could be something like 0, 1, or it could be all the real numbers, right? Because that's an open interval. Because it's you think of that as minus infinity to infinity, or anything. You know, any time you've got one of the endpoints being open, remember what that means. It means that it's all the numbers up to that, but it doesn't include that last thing. So for example, if it was the open interval minus 10, 10, again, that has no global maximum, because kind of 10, where 10 is where the global maximum is, but it's not, we've taken it away. So if you say, oh, what about minus 9.9? I say, well, what about minus 9.9? And then you say, what about minus 9.99, etc. You can always find a number closer to 10, no matter what you come up with. So that's one of the painful things about open intervals. You've got missing what's there. Well, it's a lot more wishy-washy now. Okay, so what we do is we kind of look. You have to look at behavior. Is that how you spell behavior? You spell it differently in America than Australia. Yeah, okay, because we added the U, I think. But look at behavior as a function goes to the missing endpoint. And so that usually means you have to graph it, or you have to you have to do some kind of analysis. So like for this thing here, the candidates are 0, right? 0 is a critical point, so that's always we're always going to look at that. And then we have to look at, well, what happens as it goes to minus 10? What happens as it goes to 10? Realizing that 10 and minus 10 aren't really part of the problem. So in this case here, you see 10 and minus 10. If this was x squared, the value would be 100 there. And the value there is 0. So that tells you, without looking at the graph, this tells you that this is the global min. Okay, and then this thing here tells us that there's no global maximum. So these questions are a little bit harder because you actually have to argue. This is you can see this is quite mechanical. It's like taking a derivative. You just turn the crank and out comes the answer. This one you've got to look at it. You've got to look at the graph. You've got to think, well, what's the behavior like? Is there? Okay. So what kind of questions can I ask you? So if I give you a graph, it's pretty straightforward. You just examine the graph. You can just see where the max and min is. So, for example, if we go, so we're going to close. This is our closed interval A, B. Where's the global min? It's right here. Let's call that C. Where's the global max? B. It's an endpoint, right? So the possibilities where it could have been, so these are the critical points, right? There's 3 critical points and 2 endpoints. And they're the things that you worry about. If it was an open interval, A and B, there's only a global minimum. At C, there's no global maximum.
So if it were an open interval in that case, you would just put no global maximum?
No global maximum, exactly.
You would have to put like
if this was instead of, so if this was, you know, continuing what it looked like when on this for all R, C would still be the global minimum. We'd have no global maximum now. There's no point right there. Okay, so that's one kind of problem. Typically, though, I'm going to give you a formula.
So you said the endpoints can't be local maximums, but they can be global. At least.
No, they can be, because if it was just this, let's say, okay, what are the local minimum? It's C and D. And the local maximums are A, E, and B. So the endpoints can still be a local maximum or local minimum. So the local maximum min are going to be endpoints or critical points. So yeah, we decided that these weren't critical points.
Okay.
These are the critical points. So here's a typical kind of problem. Okay, here's a nice polynomial, nice function on a closed interval. Find the global max or min. So by the principle, we know that it does exist. Okay, the possibilities for the global max or min are going to be -1/2, 3, plus whatever critical points. So let's go ahead and find them. F prime of x is 6x squared minus 18x plus 12. And I actually know how to do this. Factor that out just because I recognize it, but if I didn't recognize it, I would have used the quadratic formula. Okay, so a nice natural instinct for you to do should be to factor things. Usually you don't like multiplying stuff out. Factoring is good. And so what are the critical points? 2 and 1. So we have to test -1/2, 1, 2, and 3. So now we test them. So here's our x. So we just make ourselves a little table. Okay, so when x is 3, 2 times 27 is 54. Oh my goodness. 54 minus 81 is minus 27. Minus 27 plus 36 is 9, plus 1 is 10. Okay. 2. 8 times 2 is 16. Minus 36 plus 24 plus 1 is what? 16 plus 24 is 40. Minus 36 is 5. 1. Okay, we get 2. Minus 7. 5 plus 1 is 6. And finally, -1/2. We get what? -2 on 8. -1/2 squared is quarter, minus 9 on 4, minus 6 plus 1. Minus 2 on 4 is minus a quarter, minus 9 on 4, so that's minus 10 on 4, is what? Minus 2.5. Minus 6 is minus 8.5, minus 7.5. Okay. Although I do allow you to use your calculator. Okay, and then we just do inspection. And so what do we see? We see that this is a global max. This is a global min. What is this point here? It's a local max, right? Because it goes up and then down. And then this goes down and then goes up. This is a local min. But typically, I'm not asking about this. We're just interested in these two values. Okay, and of course, that's enough information for you to actually come up with a nice rough sketch of what the function looks like on this interval as well. That's the information that you need. Okay, so I think that's what I would call a straightforward problem. Another kind of problem I can give you is to ask for a global max or min and not give you explicitly what the function is. So I could give a problem like this. The sum of two numbers is 100. What is their maximum product? So this is one where you have to like kind of little think a bit, okay? So we have two numbers that add up to 100. So we have x plus y equals 100. What are we maximizing? We're maximizing y times x. How would we go about doing this? So when we see it like this, you're a little bit nervous, right? Because there's two unknowns, right? Because we know how to maximize things with one unknown. Can anyone see how to turn this into having just one unknown? Yeah. It looks like there's two unknowns, but they're not, right? Because x plus y equals 100, once you know one, you know the other. So there's really only one unknown. So y equals 100 minus x. So this equals x times 100 minus x. And that's a perfect, sorry, 100 minus x. Don't make mistakes with brackets, that's a common mistake. Okay, so we have our function then is 100x minus x squared. Okay, and it goes from something which is kind of a bit shaky to something that's very concrete. What about the interval?
0 to 100.
Okay, on 0 to 100. But nowhere there does it say. But what happens if, say, one of the numbers is 200? And the product is going to be negative. Right, so we can do that. Just by a little argument, we say we can ignore, you know, since only interested in both being positive. Right? Because if one is positive, one is negative, then that's not going to be big. Okay, and so you find the critical point. What's the critical point? (100 minus 2x equals 0, so x is 50, right? So our things to check up 0, 50, and 100. When it's 0, it's 0. When it's 100, it's 0. When it's 50, it's 50 times 50. It's 2,500. So straight away, we can see the global max is 2,050. If this was the minimum product, it wouldn't have an answer, right? Because now we can't throw away the other ones here. And so it's an open interval and there's no global minimum. Although I could change the number problem to be 2 positive numbers. There's lots of ways you can vary things up. So you've got to read questions carefully, especially when it's kind of like a word problem like that. These ones, of course, I find much more straightforward.